So let's start today's seminar. First speaker is Professor Gounelas from Göttingen University, and title is Curves on K3 Surfaces. Please.
Yeah, so thank you very much for the introduction, and also thank you to the organizers for giving me the chance to speak in the seminar. So I'm going to be reporting on work with first with Shi-Chen and Christian Liedtke, and then later on just with Shi-Chen. But let me begin with a bit of an introduction. To motivate some of the questions that I'll be trying to answer. So first I'll give you a definition of a K3 surface. So for me, a smooth projective surface X over the complex numbers is called K3 if two things hold. First, if the canonical divisor is trivial. And second, if H1 X OX is 0. So of course, I mean, one can make this definition of a arbitrary field as long as you assume kind of some geometric connectedness. And in fact, many of the results I'll be talking about will be true more generally of arbitrary algebraically closed fields, but I just want to keep this entire talk over the complex numbers to not have to distinguish what is true in characteristic P and what isn't all the time, and to avoid some technicalities. But if you're interested in the characteristic P case, then I'm more than happy to talk about it as well. Okay, so some examples of K3s, just to convince you if you haven't seen them before that they appear very naturally in nature. So the first example that one encounters is if I take X inside P3, a smooth quartic surface. Okay, so this is a K3 surface. And in fact, because it admits a polarization from P3, whose self-intersection is 4, we call it a degree 4 K3 surface. Okay. And another example is if I take C inside P2, a smooth sextic, and I take X over P2, the 2-to-1 map ramified along C. This is a K3 of degree 2, because in this case, I mean, I just pull back the polarization from P2 and its self-intersection will be 2 because it's a degree 2 map. So I've given you 2 examples here, but it turns out that for every positive even integer, you can give a K3 surface whose degree, namely which carries a polarization whose self-intersection is that positive even integer. So in degree 6, I mean, they have quite nice projective embeddings. They're just the intersections of a smooth quadric and a cubic in P3. And part of the story generalizes to other degrees, but eventually it gets quite hard to give explicit projective embeddings of an arbitrary K3 surface. Okay, so what are the some nice properties of K3 surfaces? Well, first, I'm just going to say this, I'm not going to write it. I mean, if you look at the classification of surfaces, K3 surfaces are the ones of Kodaira dimension 0. And I mean, well, along with abelian varieties, they're kind of the 2 major classes of Kodaira dimension 0 surfaces. So already you can see that kind of, yeah, there's quite a lot of interesting, yeah, there's a lot of interest in these surfaces because they're a big class, basically. Okay, so one first property that they have is that if rho is defined to be the dimension, or well, let me say the rank of the Picard group of a K3 surface X, then this number is between 1 and 20. Okay. So another property is basically that the moduli space of polarized K3s is quite well behaved. So let me write this down a bit more formally. If H inside pic X is ample, then h squared will in fact be a positive even integer. And the moduli space, so let me be a bit kind of imprecise here, but let me just write it like this: M2D, which is parameterizing pairs XH, where X is K3, and H is an ample, such that H squared is 2D. So this is up to isomorphism, is irreducible and 19-dimensional. Okay, so a lot of the things that I'll be discussing today really, in a sense, consequences of being able to understand this moduli space as a, as a nice irreducible space, and being able to deform K3s and curves around this moduli space, basically. Okay, and maybe I should say, why do we care about K3 surfaces? Well, perhaps I don't need to motivate this with this audience, but I mean, it turns out that they're a wonderful testing ground for many of the major conjectures of the past 100 years. So first, the Veil conjectures and even the Tate conjecture have been proven for K3s. Well, yeah, let me just write like this. And this looks a bit imprecise, but what I mean is, that Deligne proved that the Veil conjectures first for K3s and then in the general case. And similarly, at the moment, we know now the Tate conjecture for K3 surfaces, in fact, also in characteristic P, but more recently. We don't know the Tate conjecture in general. Okay, so it's somehow a class of surfaces or a class of varieties which is, not so easy that these conjectures are trivial, but also not so complicated that we have no chance of being able to prove them. So today I'm going to be talking about another set of conjectures that has to do with K3s and rational curves. Okay, so let me start a new section and define what I will mean by rational curve. Okay, so definition. I'm going to say that a rational curve on variety X is a non-constant morphism F from P1 to X, which is birational onto its image. Okay, I mean, of course, usually people define rational curves as a closed subvariety, let's say irreducible of X, whose normalization is P1. Okay, but often I'll be talking about deforming rational curves, and what I'll already be talking about, what I already mean by this is I deform the morphism, namely the normalization morphism. So I'm just going to give kind of this definition of rational curves, even though it is, of course, the exact same definition that everyone is used to. Okay, and of course, just a silly remark. I mean, if you have a variety X, it doesn't have to be that these images are smooth, right? So I can have my smooth P1 here, but I can have a morphism where the image is smooth. But of course, in general, nasty things can happen. Okay. So we're of course interested in the existence of rational curves on varieties, and this is an extremely rich. One of the things that one can say here, I mean, if the canonical divisor of X is negative, then it's known that X has many rational curves. That basically you can deform in any direction and in any way that you want. Okay. Whereas on the other hand, if the canonical divisor is positive, then the conjecture of Lang tells us that we should expect at least that if I take the union of all rational curves inside X and I take its closure, then this is a closed process of X. Okay. So in particular, if I have a variety whose canonical divisor is ample, I mean, I don't expect many rational curves. Of course, there could be infinitely many contained inside a subvariety, but I'm certainly not going to be covered by rational curves or even have them to be dense in any way. So these are the two extreme cases, and so the question becomes what happens in the middle, in particular in the case of K3 surfaces. So let me just give you one example of class of varieties in the middle. So if Kx is 0, for example, if X is an abelian variety, then X has no rational curves. Okay, so even though it is closer to having negative canonical divisor, it has absolutely 0 rational curves. So as I said, I mean, K3s and abelian surfaces are the two kind of big examples of Kodara dimension 0 surfaces. So the question becomes, what can we expect for K3 surfaces? And there's been a conjecture that's been lurking around for a few decades now. I guess it's a full. It says that a K3 surface X has infinitely many rational curves. Okay. So in particular, the union is dense. So if I have one rational curve on a K3 surface, I observe that, I mean, it cannot deform, because if it deformed, I mean, it would sweep out a two-dimensional subvariety of X. In particular, X would have to be uniruled. But since working with the complex numbers, this doesn't happen. Namely, every K3 surface is not uniruled. So each one of these rational curves, it exists in isolation. It's just, it doesn't deform at all. So this is kind of interesting in its own right, but it's also weird because it means that if we want to prove this conjecture, we're going to have to construct each and every one of these rational curves individually. I mean, essentially, you know, the statement is going to be that I can't have, you know, some technique that starting with a finite number, I can construct more and more, because usually those kinds of techniques involve deformation theory. But here, this kind of argument doesn't work. So I should say that there's a lot of similar questions to do with infinitely many rational curves on K3 surfaces. In particular, there was a famous conjecture of Yao and Zaslow that's now been proved by Phil and also by work of Shi Chen, where you want to count basically how many rational curves there exist in a particular linear system. So here I said that, you know, there's infinitely many of them on an arbitrary degree. At least this is what the conjecture predicts. But if I fix kind of a linear system, there should only be finitely many in that. Gives rise to some very interesting generating things, related to modular forms and so on. But even though we can prove those theorems, namely the Yao-Zaslow conjecture is now a theorem, it doesn't you have infinitely many rational curves on K3 for the simple reason that, I mean, it's counting rational curves, but it could be counting things with multiplicities. So if you kind of go to, yeah, it's not clear that you're not just counting multiples of the same finite number of rational curves. Okay, so let me tell you, this is now a theorem, this conjecture, and it is the proof, it is the work of many people, and more recently by Shi Chen So we completed the cases that were remaining, but I want to kind of spend a bit of time just going through the proof and giving you a rough idea of who proved what and how these arguments work, because I mean, essentially, it's a case-by-case analysis, and each case requires a slightly different proof. Okay, so the first result in this direction was a beautiful theorem by, well, it's attributed to Bogomolov and Mumford. But it only appeared in a paper of Mori and Mukai. And basically what it says is that if X is K3 and D is a non-zero effective divisor on X, then D can be written, I mean, is equivalent to some of multiples of rational curves. Okay. So of course here I'm not making any claims about what the Ni are, and I'm not making any claims about how many of these Ris we have. So it could be that an effective divisor is just written as 100 times one rational curve. But in particular, this implies that every K3 has at least one. Okay. And just from the definition of a K3, which involves that the canonical divisor is trivial and it's zero, I mean, it's not so clear how you would go from, from that definition to the existence of a rational curve. It's not that it appears somehow a direct consequence of the definition. I mean, you really have to work quite hard to construct the moduli space and to deform some rational curves inside the moduli space. So let me just tell you sketch very briefly how this works. It's a deformation and degeneration argument where, I mean, you start with a comma K3, a very special one, and you start with a very special configuration of 2 minus 2 curves on it, intersecting in just the way that you want. So here I have 2 smooth P1s. And if everything is kind of chosen very carefully, it's in the right linear system and so on, then you can deform this pair, namely union of the rational curves and comma K3, to a general K3 in the moduli space. And here, this curve becomes some singular rational curve, but it's irreducible now. Okay, and now that I have it on the general one, so let me just kind of write it like this. Now that I have it on the general K3, since the moduli space is irreducible, I can just pick my arbitrary K3 and specialize this rational curve R that I just constructed to my arbitrary K3. Okay, and here, of course, it might break up into 1,000 pieces, but I'll be getting at least one. Okay. Right. So this is roughly how the argument works for this Bogomolov-Mumford-Mori-Mukai theorem. And I mean, the ideas that we'll be using are, in a sense, similar to this, but yeah, depending on which case we're in, there's considerably more work to be done. Okay, so the next case that was important came in the late 90s, and it was a theorem of Shi Chen, roughly in 99, that says that if X is very general, then X has not just infinitely many rational curves, but infinitely many nodal rational curves. Okay, so we've constructed one on every K3, but Chen in fact tells us that if the K3 is very general, then the conjecture is not only true, but true in a very strong sense. I mean, we can find rational curves that are extremely nice. So this argument is proved by taking a very elaborate and technical type 2 degeneration to the union of two rational surfaces and constructing the rational curves there, similarly to how we constructed them in this coma case here, and then basically moving them back to the very general K3. But okay, if you look at this theorem, I mean, you think, well, we should be done now, right? Because I mean, we have infinitely many nodal ones on the very general one. Why can't we just specialize them to any K3? And actually, it turns out that this is completely not clear. And the reason is that when you specialize these curves, they could be breaking up into, sums of multiples of a finite number of rational curves. So this is what I'm going to call the specialization problem in a sense. And it's something that we're going to have to deal with to prove the conjecture in general. Okay, so shortly after this result here, we have a theorem of Bogomolov and Schenkel, which basically says the following. So it says that basically we're okay if the K3 is elliptic or has infinitely many automorphisms. Okay, so this argument is completely different to the previous ones. I mean, well, the infinite automorphism case is a bit simpler, but the argument to conclude for elliptic K3s is really beautiful. I mean, basically you have to construct, you play with the Jacobian of your elliptic, and you construct a new K3 which maps to X, and on that one you have infinitely many rational curves. And then you show that basically this gives infinitely many rational curves on X itself. So this is really not, it's not a degeneration argument, it's really using the elliptic structure. Okay, so in particular, we know now that, I mean, well, the conjecture is true if the Picard rank is at least 5. Because if the Picard rank is at least 5, then the lattice, the Picard lattice has to contain an isotropic vector, and we know that this implies that the K3 has to be elliptic. And we're also done with a very general one. So what remains is everything from Picard rank 1 until 4 that is not elliptic and has finite automorphisms. Okay, and here we were kind of stuck for, I guess, the good part of a decade and a half. And the next breakthrough was a paper of Lee and Liedtke, Jun Lee and Christian Liedtke, where they basically prove that the conjecture is true if the Picard rank is an odd number. Okay. And here, I mean, the argument is to reduce mod P for infinitely many P. So you basically start with your K3 over the complex numbers. You can reduce to the case where it's defined over a number field, and then you spread it out over the ring of integers of that number field, and then you look at infinitely many reductions of your K3. And this assumption that the Picard rank is odd in characteristic 0, well, it's a consequence of the Tate and Veil conjectures that the K3 surface over the algebraic closure of a finite field has to have even Picard rank. So basically what this is saying is that if I start with a K3 with odd Picard rank, then all of its smooth specializations will have even Picard rank. So in particular, the Picard rank has to be strictly larger than that of the generic fiber. And then in each of these characteristic PK3s, you can create a rational curve using this Bogomolov-Mumford-Mori-Mukai trick. And then you have to kind of very carefully lift it back up to the K3 in characteristic 0, and then show that basically this gives you infinitely many, if you do this for infinitely many p's, this gives you infinitely many distinct rational curves in characteristic 0. So let me just say you reduce mod p for infinitely many p and use the Tate and Veil conjectures to lift infinitely many rational curves to the generic fiber. Okay, and I should say that, I mean, this theorem is heavily based on work by Bogomolov, Hazard, and Schinkel, who proved the special case. I mean, they proved basically the case of Picard rank 1 and degree 2, but the argument they used was precisely this reduction mod p and creation of rational curves there. So it was a kind of an influential paper at the time. We're very close to finishing because we've done everything of Picard rank at least 5, and now we know all the odd rank cases as well. So what remains is namely rank 2 and 4, and furthermore we can assume that the K3 is not elliptic nor has infinite automorphisms. Okay, so this was the state of the art up until 2012, I guess. And then we have now 2 papers last year. 2019, where basically we complete the remaining cases. Okay, so what we do is we have to solve this specialization problem that I mentioned earlier, namely that if you know that on the very general one you have infinitely many rational curves, that they don't all break up into sums and multiples of a finite number of them. And then we need to kind of extend these results of Chen to more complicated Picard lattices. Okay, so let me just summarize this briefly, just to give you an idea of the 2 techniques that we prove, because essentially we prove something that also recovers the Lie-Liedtke argument in a slightly cleaner way. Okay, so the first thing is generalize Chen's degenerations for Picard rank rho is equal to 2. So I don't want to say much more about this, but basically you want to show that for any fixed rank 2 Picard lattice, the general K3 lattice, and you take an ample divisor in there, then the general K3, whose Picard group is isomorphic to that lattice, will have a nodal rational curve in that ample class that you fixed. Okay, so this is like a strengthening of this initial result of Chen that I mentioned earlier. But I mean, the proof is basically the same style, the generation, type 2 degeneration, but I mean, you have to work much harder to create the curves in the correct classes, because there's a lot more classes to deal with in the rank 2 case. Okay, but this result is really integral for both of the next 2 that I'm going to mention now that are a bit easier to explain. Okay, so the first technique is something that we call regeneration. And here, well, what's the idea? I mean, you start with a family of K3s X over some DVR. And what we want to do is we want to be able to pass curves from the special fiber to the generic fiber. So I don't want to spend too much time on this because I'd rather talk about some of the more recent things I've proven. But basically, if you have a curve in the special fiber, let's say you have an integral, a reduced and irreducible curve of geometric genus G inside the special fiber of this fibration, such that the class in the Picard group of this curve lifts to the generic fiber, then it's kind of well known by results of Rand, Bloch, and Voisin on the semi-regularity map that you can deform the curve that you started with from the special fiber into the generic fiber while maintaining its geometric genus. So this is a long and beautiful story and has to do with the twistor line. But basically, if I give you a curve in the special fiber whose class lifts the generic fiber, then we're good. You can basically deform it while keeping the geometric genus. Okay, of course, it's easy to just lift the curve arbitrarily, but usually when you lift the curve, you'll be smoothing out some of this. Yeah, you're not preserving the geometric genus. So the whole point of this gain is to preserve the geometric genus of the curve. Okay, so basically what we have to solve is the problem of how can you move a curve from the special to the generic fiber if its class doesn't lift? And this is what regeneration is. And let me just write it down. I mean, if C inside x0 is an integral, by this I mean just reduced and irreducible, geometric genus G curve, then we can, and this is the theorem, regenerate it to x eta bar after adding some rational curves. And then to be a bit more precise, i.e., there exists, what the theorem states is for an arbitrary integral geometric genus G curve in the special fiber, there exists a D inside x eta bar, so that the geometric genus of D is G, and such that the specialization of D to the special fiber contains C. So let me just say D0, which is the specialization of D, contains C as an irreducible component. Okay, so basically we start with our curve C. Its class may not lift the generic fiber, but after attaching some rational curves to this, we can build basically a stable map now whose class does lift, and we can deform that curve to some D in the generic fiber, which has the same geometric genus. Okay, so the whole difficulty here is creating these rational curves that you have to attach to C. And this is precisely what we do in the previous step, this the generation of, for the rank 2 case. Okay, so that's one thing. And in particular, I mean, what this proves is that if I give you a family of K3s over a DVR, and the special fiber contains infinitely, the generic fiber also contains infinitely many rational curves, because you can basically start, if you have infinitely many in the special fiber, you can take one, you can regenerate it, take another, you can regenerate it, and then there's a bit of a Hilbert scheme argument to show that you really get infinitely many on the generic fiber as well. Okay, so this also gives a kind of a cleaner proof of this theorem of Lee-Liedtke for the odd case. Okay, so that's one of the two techniques. And the second one, which I'll again only sketch, is we want to solve the breaking up problem. Which I described earlier. Namely, if I know that the very general K3 has infinitely many rational curves, when I start specializing them to an arbitrary K3, they could break up into sums and multiples of only a finite number of such curves, so I cannot prove that every K3 has infinitely many. Okay, and the solution to this is something that we call the marked point trick. And basically the upshot is the following. and this is the theorem basically, that if lambda is a K3 lattice, and L inside lambda is primitive and ample. So primitive is important here. And assume that we know that for X inside the moduli space of lambda polarized K3s general, there exists a rational curve inside this primitive ample class L. Then the same thing is true for an arbitrary K3 inside this moduli space. Well, sorry, I should be more precise. Then the same thing is true for every K3 whose Picard group is isomorphic to lambda. Maybe let me call this Y. There exists an integral rational curve in L. Okay, so in particular, if my class is primitive, then this specialization, it doesn't break up. That's what I'm saying here. Okay, so let me tell you kind of very briefly why we call this the mark point trick. Well, for one, because it's a catchy title. So basically what you do is you start with your point Y in the moduli space, and you take a very general curve, kind of joining it to a general point X inside ML. And then you put this inside some kind of general surface U inside M2D, so that this curve here is the intersection of the intersection of U with M lambda. Okay, so now we know that on X there exists a node, well, not a nodal, but there exists a rational curve in L. So what we do is we take this rational curve, we spread it out to the entire moduli, this U, and then we try to restrict it to Y and show that it is irreducible here. That's what we want to do. But this works by basically you decorate your family of curves with 4 marked points. And what this allows you to say, to conclude, basically, is that the locus where the specializations of these curves are not irreducible has to be divisorial inside U. So you get some divisor where this curve could potentially split. But if it splits, then because the class is primitive, you generate the whole Picard group, so it has to be this entire Noether-Lefschetz locus. But because we assumed that the initial was irreducible, you get a contradiction. So that's roughly, very briefly, how the argument goes. But I mean, it's called a mark point trick because you have to kind of decorate your family of rational curves with 4 sections, and then you get a map to the moduli space M04 bar. And because the complement there of, because the boundary there is ample, you can basically show that, the locus inside this U is divisorial, where the rational curve might split. And this is kind of what we need. Okay, are there any questions about this so far? Okay, I apologize. This was very, as I said, it's a case-by-case analysis, and of course we'd like a more elegant proof which deals with all the cases simultaneously, but unfortunately at the moment, every one of these cases kind of has a slightly different technique and certainly would warrant, its own talk in each case. But I just wanted to give you an overview of how this conjecture has now been proven. Okay, so that proves this conjecture here of existence of infinitely many rational curves on an arbitrary K3 surface over the complex numbers. So let me now kind of change direction a bit and talk about what we know for higher genus curves. Okay, so in this paper with Shi Chen and Christian Liedtke, we also proved that basically the following theorem. That if X over C is K3 and G is some non-negative integer, then there exist curves Cn of geometric genus of Cn is equal to G that we fixed, such that the intersection number as n goes to infinity of Cn with some fixed ample h is equal to infinity. Okay, so this is kind of a fancy way of saying if G is 0, I mean, you have infinitely many rational curves, but for high genus, I mean, this is really saying that you have infinitely many divisor classes whose linear system contains a subspace parameterizing curves of geometric genus G, okay, for arbitrary G. And why do I state it in this funny way? Well, if I give you a genus G curve on a K3, there's this amazing fact that basically each reducible geometric genus G curve C inside a K3X, it deforms in a G-dimensional family. Okay, so if I have a genus 1 curve, so when I say genus 1, I mean an integral closed subvariety of X whose normalization is a smooth genus 1 curve, then this will deform in a one-dimensional family, all of whose members have geometric genus 1. Okay, so in particular, if I say that, if I know that I have one genus 1 curve, then I have infinitely many because this one has to move. So the statement that, you know, every K3 contains infinitely many genus 1 curves is much easier than, you know, you just have to construct one and then you're done. So what this theorem says is that basically you can construct them in infinitely many distinct classes. Okay? And in fact, moreover, one can do this for arbitrary genus. Okay, but one thing that is not so clear here is what happens to the arithmetic genus of these curves. So indeed, the intersection of these curves with an ample goes to infinity, but we'd also like to show that Cn squared goes to infinity. Okay, so that's one question. And perhaps the more interesting question is, well, as I just said, I mean, every genus G curve deforms in a G-dimensional family. What can we say about the deformation moduli of this family? So what is the variation? In moduli of the above constructed curves? Okay, and by this I mean, well, you know, I start with an integral curve of geometric genus G, I put it inside a family with a G-dimensional base, and I look at the normalization map, which takes a point in that base and sends it to MG, and I want to know what is the dimension of the image of this map. Right? So I have the base of the family mapping to the moduli space, and I would like to say, well, is, for example, the variation maximal in the sense that is this, if the base is G-dimensional, is its image also G-dimensional inside MG, which would mean that basically in this family we have maximal variation moduli. It's not an isotrivial family, it's the exact opposite. Okay, so this is completely not clear by the construction that we had in our paper last year. And we worked on this with Shi Chen and proved the following theorem. Basically, it says that, in fact, there exist Cn as above, well, sorry, let me write this a bit differently. So if G is at least 0, so not the 0 case, then in fact there exists Cn as above, such that Cn squared goes to infinity, and the variation in moduli of each Cn is maximal. Okay, so what this proves is that an arbitrary K3 has infinitely many families of curves of geometric genus G, which move in a maximal sense in moduli. Okay, and this Cn squared goes to infinity. I mean, of course, it implies that Cn dot H goes to infinity by the Hodge-Index theorem. So it's a strong condition. Basically tells us that also the arithmetic genus, so that the number of singularities is also increasing. And this was not clear from the previous theorem. Okay, so let me give you a very brief proof. Basically, to prove this, I mean, we assume that the K3 has infinitely many rational curves. So I wrote here that the genus is at least 0, so we don't know whether we can find curves of arbitrary arithmetic genus, but geometric genus 0 on the K3. Okay. So assuming, nevertheless, that a K3 has infinitely many rational curves, which was proven by the theorem above, we will now kind of use these rational curves to construct higher genus curves whose arithmetic genus goes to infinity and which have maximal variation moduli. Okay, so let Ri be infinitely many rational curves in X. Which, as I said, we know now because of the resolution of this conjecture. And now we take y di, a log resolution of x Ri. Okay, so di now simple normal crossings divisors, and y is just the blow up of x at a certain number of points. Okay, so in this case, the logarithmic Bogomolov-Mijalka-Yau inequality it basically tells us that for each I, well, okay, sorry, there should be an I here as well. I mean, the y depends, of course, on Ri. So kyi plus di squared is less than or equal to 3c2 omega yi log di. Okay, so this is just the logarithmic Bogomolov-Mijalka-Yau inequality for such a simple normal crossings pair. But we can translate both sides of this inequality, namely this side and this side, into statements about the types of singularities that the curves Ri had, like how many, the kind of invariants that come in, how many singularities you have, the multiplicities, the number of branches, and so on. And if you kind of play around with what it means to resolve these singularities, then you basically can rewrite these intersection numbers and the C2 in terms of these invariants of the curve. Okay, so this inequality basically translates to, and this is a bit of work, but I'm not going to get into it, but it translates to into the following two facts: that if Ri squared is big enough, then Ri has a locally reducible singularity. And on the other hand, because we don't know whether Ri squared goes to infinity, one can also rewrite this as basically that it suffices to know that this intersection number of two distinct rational curves is large enough, and this does happen, to conclude that Ri and Rj meet in at least two distinct points. Okay, so I mean, a small remark here. I mean, it's weird because we construct infinitely many rational curves, and each one of them has to be constructed by hand, right? I mean, you see it from this list of proofs that I gave earlier. I mean, every curve, every one of the infinitely many rational curves on a K3 is basically constructed by hand. I mean, one by one, you have to construct them. But it's really often not clear what these rational curves look like and how they intersect. So, I mean, it could be that all of them pass through one point and they have no other I mean, you know, we have no control over such general questions. So we really have to use something like this log inequality to conclude that, you know, if the intersection number of two of them is large enough, then, you know, they meet in at least 2 points. Okay, so now basically if you know that one rational curve has a locally reducible singularity, or that two of them meet in at least 2 points, then you can degenerate these guys to something of higher genus. And in fact, something of higher genus which has maximal variation moduli. So we can deform Ri or Ri union Rj. You know, this will look like whatever, something like this, and this will look like this, to a higher genus curve maximal variation. Okay, so that's a very rough sketch of the proof. And I mean, you might ask, okay, what have we really gained here? And I want to try to convince you that actually we've gained a lot. So the existence of infinitely many rational curves on K3s is somehow, you could try to motivate it in terms of this Lang conjecture, or in terms of, you know, an analog of existence of infinitely many rational points over number fields. But I mean, how is this really a result that one can use in geometry? I mean, okay, K3s have infinitely many rational curves. I mean, what am I going to do with them? And the problem, I mean, the reason why they're not so useful is because they don't deform, right? I mean, they're completely rigid. We don't really know where they lie and what they look like. So they're hard to play around with. But now these higher genus curves actually turn out to have very interesting properties. So let me just give you one corollary, which is immediate from this, is that any K3 X over C contains a genus 1 curve which deforms non-isotrivially. Okay, so of course, in fact, the theorem tells you that there's infinitely many of these, but I'm going to try to convince you that even the existence of one of them has very interesting applications to the geometry of K3 surfaces. Okay, and of course, you know, just if you've seen this before, I mean, it's not difficult to show that every K3 contains a genus 1 curve, but you have no control over whether it deforms isotrivially or not. Okay, so really, this is the new thing, which is completely not clear from the old proof of existence of one genus 1 curve. Okay, so let me now just give you two quick applications, and I'll stop then. I'm not going to prove them, of course. Okay, so the first application is the fact, which was proven by Kobayashi, that basically says that K3s have no global symmetric differentials. But the proof of this given by Kobayashi was analytic in nature, and I mean, it uses the resolution of the Calabi conjecture by Yao, so it's really a deep result. And
yeah, vậy mới là đâu vẫn ở Toulouse hả hay là
I guess that's not a question. Okay. So we obtain a new proof of the fact that H0x sim k omega 1x is 0 for every k bigger than or equal to 1, and this proof is now algebraic. Okay, so that's one application of just this existence of one genus 1 curve which moves non-trivially. And the second thing is it implies a conjecture of Huybrechts and this, I mean, to conclude this conjecture of Huybrechts, we also use a result of Voisin. I mean, basically, yeah, Voisin did most of the hard work here. We just, knowing the existence of one genus 1 curve which deforms non-isotrivially, I mean, that with what Voisin proved concludes this conjecture of Huybrechts that basically says constant cycle curves of bounded order are dense in the classical topology. Okay, and I think I'm going to stop there. So many thanks.
Thank you very much. Are there any questions or comments?
So if C square is bounded, do you still expect to find infinitely many rational curves on K3 surface?
Well, I mean, we know that there's infinitely many rational curves on K3 surfaces, but we don't know that the C squared of them is bounded. I don't know if, yeah. It's not that, you know, C squared being bounded would cause problems, right? We know it for independent reasons, and then we can't control whether the arithmetic genus of these curves that we create goes to infinity or not.
May I ask questions?
Mm-hmm. Yes.
So you construct infinitely many rational curves for all projective K3.
Yes.
Are there, can you say about the singularities? So can you some only nodal one?
Oh, you mean no? If the K3 itself has singularities? You mean if the K3 itself has singularities, or to say something about the singularities of the curves?
No, singularity of curves.
Yes, yeah. Basically, not really. You know, it would be optimistic to expect that on an arbitrary K3 you have infinitely many nodal rational curves. I mean, I'm not sure I believe this.
That is too optimistic.
Yeah, I don't know. I mean, I don't want to say anything too strong in any direction, but I mean, basically the best thing that we can say at the moment is, you know, things like this thing here, that basically, you know, if the intersection number is large enough, then at least you have a locally reducible singularity. You don't just have cusps everywhere. I mean, but essentially to answer your question is I have no idea. I mean, this is a hard and interesting question to control the singularities.
And can one reduce, or can one say something about the positive characteristic?
Yes. Okay, so thank you for asking. So basically, we prove the conjecture also in characteristic P, other than a few strange cases in characteristic 2 and 3. So basically, the claim is that if I give you a K3 surface over an algebraically closed field of characteristic at least 5, then it also has infinitely many rational curves. And in fact, the proof is very similar to, you know, all of this that I sketched here. I mean, you have to use Bogomolov-Chinkel to get the elliptic case, then you have to use something like Lee-Liedtke, and then you also have to prove, you know, the regeneration and the mark point trick business to pass curves from characteristic 0 to characteristic P. But basically, the conjecture is known in characteristic at least 5, and in characteristic 2 and 3, there are very, very few cases that we don't know, namely the cases where the K3 is isotrivially elliptic. So yeah, we haven't thought about those, but it seems to be slightly hard. I don't know. And for high genus curves, we can only prove this theorem here for genus 1 curves in characteristic P. So we can't prove it for high genus, for genus higher than 1, but basically the conjecture is known for genus 0 and 1, let's say, if the K3 is, yeah, in characteristic at least, yeah, 5.
Thank you. Are there any other questions or comments?
So in which cases the union of these curves are dense for the classical topology?
Yeah, this is of course another big question. We have no idea. I mean, it's, you know, it's conjectured that rational curves are dense in the classical topology as well on every K3, but this is not known, and our argument gives nothing in that direction. So Shi Chen and Lewis have a paper where they prove that if the K3 is kind of extremely general, then this is true, but that's basically the best result in that direction, namely the analytic density of rational curves. So the only kind of density that, and this is, I think, kind of part of the motivation of this conjecture of Huybrechts. I mean, okay, we don't know that rational curves themselves are classically, analytically dense, but what is another weaker thing that we can ask? And that is these curves of these constant cycle curves, which are kind of higher genus analogs of rational curves. But yeah, I don't want to get into this.
Are there any other questions or comments? Then thank you very much again for your beautiful talk.
Yeah, thank you. Thank you for having me and for listening to the talk. Thank you.